Yeah, it's a pleasure to be here. I'll be talking about granular flows. So traditionally in condensed matter, one is dealing with liquids, with solids and gases. And these phases depend on the temperature. Now granular matter, also commonly known as sand, cannot really be classified into these categories. And in this half an hour, I try to give you some examples that you may be familiar with, but the explanation of which is maybe not so obvious. And it's one other thing that I would like to point out is that much of the what we know about sand and other granular matter actually came about only in the last couple of decades, which I find personally quite surprising. Yeah? So there was a time where we knew more about the atom than about sand flow. So what is sand? Well, you all know sand. It's a collection of macroscopic grains. You have sizes from 10 microns to a millimeter. Below 10 microns, the Brownian motion sets in, and then you can't really think of it as granular matter anymore. And you have solid friction between the grains and inelastic collisions. So it's a very dissipative system. Yeah? So if you don't externally force it, it comes to rest immediately. Yeah? And now this may not sound so wild and interesting, but what makes it actually difficult, the subject, to study, especially theoretically, it's far from thermal equilibrium. Yeah? So if you have a gas, for example, which is in thermal equilibrium, you can unleash the power of statistical mechanics on it, yeah, to get state variables and so on. But you cannot do this with sand. Yeah? And this makes it difficult to predict. Yeah? Now, as I mentioned earlier, sand is not really a liquid, neither a solid. It can behave either way. So, for example, in an avalanche, you have a liquid-like region and you have a solid-like region, and they coexist. Yeah? So you don't have that in ordinary water. If you stir a cup of water, all the molecules will flow, whereas where you do it with sand, most sand grains will just stay put. And you can walk on the beach without sinking in. On the other hand, you can make it flow like here in this hourglass. Yeah? And now why should we care about this? Well, in times like these, it's worth pointing out that there's some economic reasons. Yeah? For example, during the manufacturing process of up to 80% of products, some sort of powder is used. Yeah? Just think of pharmaceuticals, for example, or chemical industry. And if you don't know how it flows, if you can't predict this, which we cannot really, I mean, there has been progress made, but we don't really have a full theory like in hydrodynamics, then you cannot make it efficient. And so a lot of things in industry are really trial and error. Yeah? Sometimes they use a hammer to unjam some pipes where grains flow through, and so on. And from a physical point of view, it's actually also interesting because the structure of a sand pile is really the same as in a glass or in a liquid. Yeah? And this kind of study has been pioneered by Bernal, a famous Irish physicist, who studied basically packings of spheres, and we actually just had a conference a few weeks ago on that. Yeah? It's a disordered packing, and if you look at the structure of the molecules in a glass, yeah, which is a liquid with a very high viscosity essentially, then it's essentially the same kind of structure. Yeah? So people like to use these kind of systems as a model system for glasses. Now, let me start off with a very simple example. Yeah, you all know drainage from an orifice of water. Yeah, and there's Torricelli's law, which is probably one of the oldest laws in physics, 1643. Yeah, you can derive it from Bernoulli's equation, and that came 100 years later. But okay, so this is obviously the flow velocity here depends on how high this water column is. Yeah, so there's nothing special about this. And then somebody had the good sense to do this for sand, yeah? Like hopper flow or something like that. And this happened more than 300 years later, yeah? Last century, 50 years ago. And this is now the flow velocity of sand when it drains from a reservoir. Now, this looks similar. I mean, you don't have to worry about the details here. but the one thing I'd like to point out here is this depends on the height of the water column, and this does not. So you could make a granular column 10 kilometers high, and you would still get the same flow rate out. Yeah? And this is quite astounding. And why is that? Well, if you put a pressure sensor there and you fill more and more sand in, what you will see is that the pressure will initially rise, what you would expect. Yeah? So if this was water, this would rise linearly, of course. Yeah? But this will actually saturate at some point, and the pressure will not increase anymore. And, well, how can this be? I mean, where does the weight go of all the grains? And what's happening is that the pressure distribution inside a granular medium is highly anisotropic. So this picture here is from Bob Berenger's group in the US. So they pioneered the study with photoelastic discs 20 years ago. So these are discs which you put through a cross polarizer, and if a force is if they're deformed, then they essentially rotate the light, and so high forces appear bright. Yeah? So these are a lot of tiny discs, two-dimensional, and gravity is acting on them. And you can see that you have basically these so-called force chains, where a lot of force is carried by the particles, and you have large regions where essentially no force is felt by the particles. And these terminate at the walls. So what's happening is that essentially the weight of this sand pile is carried by the walls. Yeah? So it's some kind of arcing effect. And this is useful to know, for example, if you would like to store some grains in a silo, and there have been many incidents where this has been a problem. Yeah? Where the walls just were not strong enough, and a silo just burst. And of course, this is also the reason why in an hourglass we use sand, because the flow rate is independent of the column height of the granular medium, and so you can make your markings at equal spacings. So let me continue with the example and see what's happening when the grains flow out of this orifice, and you get a granular jet. Yeah? So let's consider first what's happening with the water jet. Now here is just water coming out of a funnel, and you can see that the water jet becomes unstable, yeah, and forms droplets. And this is the famous Rayleigh plateau instability. And the reason for this is surface tension. So surface tension is a thermodynamic effect. So here, if you, these are supposed to be molecules in a droplet, but basically, energetically, it's more favorable for the water molecules to be surrounded by neighbors. The water molecules near the surface are unhappy because they have less neighbors. As a consequence, the liquid tries to minimize its surface area, and if you have just a droplet, it tries to make a sphere, yeah, because it's the least surface area for a given volume. And this is the reason why this becomes unstable. There's always some kind of perturbation, and you can make a calculation, which is a bit nasty, but possible, yeah, where you look at the modes of perturbation of this interface, yeah, and look at the surface area at constant volume. And Lord Rayleigh did just that, and you will find that there's a wavelength at which you minimize the surface area for a given volume, and it's about of the order of the jet diameter. So this mode will grow, and then eventually this will pinch off into droplets that are about the size of the jet. Yeah. Now you can do the same thing with sand. Yeah? In this case, 100 micron glass beads, and what you would expect is nothing, yeah? Because sand does not have surface tension, it's athermal. Thermodynamics plays no role. So, but what you will see is the following, and I hope this works. No. So here we dropped a 100,000 euro high-speed camera from 2 meters height. Yeah? Of course, we made sure somebody caught it, yeah? And it's so co-moving with the granular jet. So this is what you see, nothing special, but now droplets form. Yeah. So this is about 2 meters now, and well, then it lands in a soft bed of styrofoam. But how is this possible? Yeah, I mean, there's no surface tension, so how can this be? And it's pretty generic. What you can also do is you can take the same kind of material and drop a steel ball in. You have to fluff it up, and so the steel ball is coming. Yeah, it's 1-inch steel ball, and you get this huge jet. Yeah. So this is something you can do in the classroom. I mean, the grains have to be really small, and you have to fluff it up. It shouldn't be compacted, but it's a huge jet. Yeah, and again, the jet becomes unstable and forms droplets. And this is very odd, and but it doesn't always happen. So you can take 100-micron copper beads instead of glass beads, and do this. And this is now pretty boring because nothing happens, although it's the same size. Also, air does not play a role, so we evacuated this, and it doesn't matter. Yeah. So how can we explain this? And essentially, the answer lies in, well, I mentioned the word nano now, nanonewton forces. So you can control the cohesion by coating these grains with nanoparticles, silica nanoparticles. And what they do, they basically, it's like a spacer, yeah? So they cannot come so close together, and they're very tiny cohesive forces between particles. There's van der Waals, and there's condensation of water on the, so tiny capillary bridges. And these forces are of the order nanonewton. You can measure this with an atomic force microscope. And by basically changing these forces by roughly a factor 2, yeah, decreasing them, you can make it disappear. Yeah? So we're talking about tens of nanonewtons here. Yeah? So by changing this by 10, 20 nanonewtons, you make this clustering disappear. Yeah? And this is quite surprising that you can tune this macroscopic effect with such tiny forces. Yeah? I mean, this is not the whole story. I mean, then somebody did simulations on this, and the restitution coefficient also plays a role. So essentially, that's basically how much energy is lost during each collision. And then you can make a phase diagram of the restitution coefficient versus cohesion, and you'll find there's a region where you get droplets, and there's a region, for example, with the copper beads, where you don't get that. Yeah? And so this is quite nice. So this tiny force can really tune this effect, and this is basically due to these two effects, inelastic collision and cohesion. You can also calculate sort of an effective non-thermodynamic surface tension, which is essentially the depth of the work done required to overcome cohesion divided by the particle diameter squared, and it's 5 orders of magnitude less than in an ordinary liquid. And also this may also be helpful to understand planetary formation, where you have dust attracted with gravitation, and it has to form clumps. Yeah? So this is also still, there's still open questions, and this may illuminate some of these processes. Now, another effect, granular effect that is quite famous, and I don't know if you heard about this, is the Brazil nut effect. Yeah? So this is, happens when you buy a muesli and you open it, yeah, and you find that all the large nuts, the Brazil nut, yeah, is on top. And now this problem goes beyond mueslis, yeah. So if you're if you're in industry and you want to make aspirin, yeah, you have different powders that you want to mix together, and they come in different sizes and shapes. And obviously you don't want to over or underdose the active ingredient, so you want to mix it, yeah. But if you just shake it, it will separate according to size, yeah. So it is and it's also counterintuitive, because you would imagine that the big stuff would go to the bottom, yeah. So people have known about this for 100 years, but it's I mean, there are many different effects going on, and I will tell you about two. One is granular convection. Yeah? So this is a magnetic resonance imaging. So we went to Indian supermarket, bought some poppy seeds and some Rajagara seeds. The poppy seeds have oil, so you see them in the MRI. And you tap it, you take a snapshot, you tap it, you take a snapshot, and then you can make a movie. And this is a cylinder full of seeds. And you see that there's a convection roll, which is induced by the friction with the walls. Yeah? And so this is also what happens when the muesli is transported. Yeah? You get a convection roll, and that essentially drives the particle up to the top. And if the particle is bigger than the downward stream, then it stays there. Yeah? But it's actually not that simple, because if you change the density of that big ball, then and you measure how long it takes to rise to the top, you see this. Yeah? So light balls go up very slow, fast. This intermediate density really slow, and the really heavy ball, the steel ball, goes up really fast. Yeah? So it goes up by a factor of 10. It goes up faster. Steel ball in this glass bead bed. Yeah? So how is that possible? Well, it turns out that air is responsible for this, and this is one way to illustrate this. If you take a 1-inch plastic ball and a 1-inch steel ball, and you tap it, you see this. Yeah? And this is just to show that air drag really doesn't matter. They're so big and heavy that it really doesn't matter. They go up the same height. Now you put them in a bed of glass beads 0.5 millimeter diameter. Yeah? So you just embed them halfway in there, and you tap it again. And now watch what's happening. So right is steel, left is plastic. Yeah, it gets sucked in. Why is that? Because the bed is like a porous plug, yeah? And air has trouble going through it. So when you tap it, you get a huge pressure gradient, yeah? Which is quite considerable, because you get a low pressure region at the bottom, because the pressure cannot be equalized so quickly. And so you get huge pressure gradient, first in one direction, then on the way down in the other direction. And there's some asymmetry. I don't want to go into details, but essentially it conspires to give you this funny curve that I just showed you. Yeah? And so the upshot here is that essentially by evacuating the bed, you can get rid of this effect. And if the particles are not too big, it promotes mixing. Yeah? So this is one way to get mixing. How much time do I have? Oh, okay, so then finally, this is my final example, is foams, because I'm in the foams and complex system group. So some of this work also has been done here while I was here. So as you wouldn't think of foams as granular matter, yeah, it's air bubbles in water, yeah, and of course they also have some industrial applications. But essentially, there are a lot of similarities. You can think of them as soft sand, yeah. Instead of solid friction, you have viscous dissipation between the bubbles, yeah, and they're much softer than grains. So one typical example, shaving cream. Everybody knows shaving cream. I didn't want to make a mess. I made that mistake once, so I made a movie. It's like solid-like, but you can also shear it, yeah. And the funny thing is, 95% of this is just air. 5% is water, and then some soap, some surfactant, which stabilizes the foam. So how is that possible that it has this behavior, even though it's mostly air and just a little bit of water? And I just want to sort of explain this. This is also when you shear, this is a two-dimensional foam. When you shear it, yeah, and this is the bubble trajectories, so the top view, and you can see it's quite a complicated, erratic, intermittent motion. Yeah? And characterizing this is one of the challenges we face, and we're thinking about it very much. But just to explain you why foams are so viscous, so if you take ordinary water, it's a Newtonian liquid, so the stress or the force you apply is proportional to the deformation rate, which is defined here. Yeah? So it's just this, if you take a piece of liquid and deform it, that's delta L over L, it's the strain, and the time change is the deformation rate, the strain rate. And so the stress is proportional to the strain rate and the proportionality to constant the viscosity. Yeah? This is a Newtonian fluid. Now, if you take that same solution and you bubble air in there, you get a foam, but now the stresses at the same shear rate are orders of magnitude higher, yeah? Even though it's water. And the reason essentially is because dissipation is now in the thin films. Yeah? So when you calculate the effective shear rate, is not the velocity divided by the distance between the bubbles, but the velocity divided by the film thickness, which is a micron or less. Yeah? So the effective shear rate in that liquid film is 5 orders magnitude or more higher than the shear rate you would see and measure. Yeah? And this is the reason why you need much larger stresses for a given shear rate. But it's not so simple because there's also, the viscosity is not a constant in this material. It depends on the shear rate. And also there is what's called a yield stress. So below that yield stress it doesn't flow and it's just an elastic deformation. And this is why shaving cream doesn't flow out of your hands. Yeah? And this can be empirically fit, and people do that all the time, but there's no theory that really predicts that curve. Yeah? And of course in industry when you make these things, I mean, you would like to predict this. Yeah? And so a lot of work in recent, we've done a lot of simulations of this as well in recent years, and I don't want to go into detail, but this is just one example of a so-called complex fluids. There are other examples like blood, colloidal suspensions, emulsions. For example, cornstarch and water. Yeah, very tiny particles suspended in water is a colloidal suspension. And here you get the opposite effect that the viscosity is increasing with shear rate. Yeah? And this is now used, for example, for bulletproof vests and stuff like that. So this is sort of the area of complex fluids, and trying to understand this behavior is quite challenging. Yeah? Which brings me to the conclusions. What I haven't really mentioned is, and I think this is also the reason why some of this progress only has been recently made, is that even though it's an everyday material, sand, it's opaque. Yeah? With water, you can put tracer particles in there or dye and follow the streamlines and make measurements. Sand is opaque, or suspensions, and if you want to measure the flow field, you have to actually do some tricks or use some expensive machinery, yeah? Or do two-dimensional experiments. And theoretically it's challenging because often the stuff is out of thermal equilibrium. Yeah? Not everything, but so colloidal suspension, there's the thermal, but granular media are not in equilibrium, and you cannot use anything that has to do with entropy, thermodynamics, and so on. So, well, thank you for attention.